These are today's topics, all from section 1.2. Orders of convergence. Then compare two sequences. Then the third topic is compare two functions. Topic 1, some terminologies are often used. Some terminologies are often used to describe how fast a sequence converges to some number. Take a look at the following examples. Say now we have 3 sequences. The first one is xn. Xn is 1 over 1 plus lateral log of n. The first term of this sequence is when n is 1, first term, first number, lateral log of 1. When n is 2, second number, 2. When n is 3, third number is this, and so on. Yeah. This notation means this sequence. Now, second sequence, yn is 1 over n squared. First term is 1 over 1 square, 1 over 2 square, 1 over 3 square, and so on. The third sequence is Cn. It is 1 over e to n, the general term. First number is 1 over e, 1 over e squared, 1 over e to the third. It is easy to see that all these 3 sequences converge to 0. As n approaches infinity, xn, n, not x, 1 over 1 plus lateral of n. The limit is 0. When n approaches infinity, yn also converge to 0. N approaches infinity, Cn. 1 over e to n converge 0. All the 3 sequences converge to 0, but at different speed. How to see they converge to 0 at different speeds? Let me make a table. Then we will see. Take a look at this table. The first column is n. Second column is xn, 1 plus lateral of n. Third column is for the sequence yn. And the last column, Cn, 1 over En. When n is 1, xn is 1, yn is 1, but Cn is upon 36, 78, 79, 44, 1, 2. When n is 2, xn is 0.5, 90, 61, 661, 091. And YN 0.25. CN is a 0.1, 35, 33, 52, 83, 2. SN is increased. It seems that YN and CN converge to 0 faster than XN. More data. Say N is 10. XN is 30, 27, 93, 10, 6, 6. YN is 0.01. CN is 4.5, 39, 99, 29, 8 times 10 to -5. So CN converges to 0 very fast. How about N is 20, 0.25, 0.26, 70, 1, 7, 8. YN is 0.0025 and CN is 2.06115362 times 10 to -9. Very small. How about 100? XN is 0.178, 46, 715. And YN is 1 times 10 to -4. And 3.72, 007598 times 10 to -44. So clearly, as n approaches infinity, yeah, all xn, yn converge to 0. But clearly, Cn, this sequence, converge to 0 fastest, and Xn converge to 0 the slowest. Now, let me introduce some concepts to describe how fast a sequence converges to a number. To study mathematics, definitions are most important. So always, remember definitions and understand definitions. Now, let me introduce definitions. Suppose we are given a sequence. Let be given a sequence x1, first term, x2, x3, and so on. Suppose these numbers are real numbers, okay, all are real numbers. And suppose xn as n approaches infinity, xn approach some number x star. Now let me introduce definitions about the convergence speed of this sequence. The first one, xn minus 1. If I consider xn minus 1, the current number minus x star, then take absolute value. This is the distance of the current number from the point x star. If current distance over the previous distance, this is a new sequence. When n approaches infinity, if this ratio approaches some number c, where c non-zero and positive, but less than 1, then this case, we say that let me give a name to this limit. Let me call it 1. Then we say that the rate of convergence of the limit 1 is linear. When we say that this sequence of numbers converge to x star linearly, that means that this limit is true. The current distance over the previous distance when n approaches infinity approach some number, the number less than 1 greater than 0. Because of this limit, let me give a name to this limit. Let me call it say 2. Okay. 2 implies that this distance over this distance roughly is c when n is large enough. Left-hand side is a ratio. Let me move the denominator to the right side. Okay, which further implies that the distance of the current term roughly is c times xn minus x star. Because since c less than 1, the current distance is surely smaller than the previous distance. Yeah, this is what the limit number 2 says. The current distance less than the previous distance by a factor of c. C is a number less than 1. Then the convergence is linear. Now, second, okay, go back to the example 1. Go back to this example. Yeah. We have 3 sequences. Which one converge to 0 linearly? Take a look. Definition is here. Definition is here. Definition. Okay. In example 1, in example 1. Okay. Let me consider the Cn first. Cn n plus 1 minus 0 over Cn minus 0. Then let n approaches infinity. This is n approaches infinity. Cn is 1 over n e to n plus 1 minus 0. Then over absolute value en minus 0. Now cancel en from the denominator and from the numerator. Then I get limit n approaches infinity 1 over e. Then this limit is 1 over e. E is 2.8 something. So 1 over e, of course, greater than 0 and less than 1. So conclusion is, so the Cn sequence in example 1 converges to 0. How fast? Linearly, at a linear rate of convergence. Linearly convergence is not very fast. It is fast, but not very fast. Okay. In there are many examples. A sequence converges to some number faster than linearly. Okay. How about the sequence xn? Let me compute. Okay. Xn plus 1 minus 0 over xn minus 0. Then n approaches 0. Let me determine this limit. This is a limit n approach infinity 1 over 1 plus lateral log n plus 1 minus 0. Then over 1 over 1 plus lateral log n minus 0. Absolute value. And this function is equal to, easy to see that it is equal to 1 plus lateral log n over 1 plus lateral log n plus 1. I want to determine this limit. How to find this limit from calculus 1? I can use L'Hopital's rule because the limit is indeterminate limit of the type infinity over infinity. I can use L'Hopital's rule to find the limit. It is take derivative on the numerator with respect to n over derivative with on the denominator n plus 1. Then the derivative on the top is 1 over n. Derivative on the bottom by chain rule 1 over n plus 1. This is limit n approaches infinity 1 plus n plus 1 over n. It is 1 plus 1 over n. So the limit is 1, not less than 1. 1. Therefore, this case, we say that xn, this sequence, converges to 0 worse than linear. The convergence rate of this sequence is worse than linear, because this number not less than 1. This limit approaches 1. That means that when n is large enough, current distance to 0 roughly is equal to the previous distance. So convergence very slow. Very slow. Okay. How about the sequence yn? Let me compare this limit yn. Yn plus 1 minus 0 over yn minus 0. Then take limit. It is what is yn? N approaches infinity. 1 over n plus 1 square minus 0, absolute value. Then over 1 over n square minus 0, absolute value. And it is easy to see that this function is 1 over 1 plus 1 over n squared. So n approaches infinity. 1 over n approaches 0. Therefore, the limit is 1 over 1 minus 0 squared, 1. Again, this sequence, the conclusion is converges to 0, worse, converge to 0 worse than linear. So from by using this definition, we see that the C sequence converges to 0 fastest. The rate is a linear rate. This is a linear convergence. Now, definition 2, better than linear. How to describe a sequence converge to 0, converge to the number x star, better than linear. Definition number 2. Number 2. Still consider this limit. Which limit? The limit is this limit. Still consider this limit. The limit in 1 in equation 1. If xn plus 1 minus xn star x star over xn minus x star absolute value. Now take limit. If the limit is linear, in linear, the limit is some number greater than 0 and less than 1. Now, if the limit is 0, this case, we say that the rate of convergence of the limit in equation 1 is superlinear. Superlinear is superlinear. Faster than linear. Faster than linear. This is definition number 2. Definition number 3. Still consider the limit in equation 1. If this ratio xn minus 1, xn plus 1, yeah. If I consider xn plus 1, the current term, that is the distance between the current term and the point start. The current distance, I compare the current distance with the previous distance. Square. Previous distance usually less than 1. Now take square. Very small. Now I compare the current distance with the previous, the square of the previous distance. Now I let n approaches infinity. If the limit is c, what is c? A number. What number? It doesn't matter. Okay. C, any positive number. Any positive number. We don't need c less than 1. Then in this case, we say that the rate of convergence of the limit in equation 1 is quadratic. Quadratic, of course, faster than linear. A quadratic convergence must be superlinear. How to see a quadratic convergence must be superlinear convergence? Let me prove. Okay. According to the definition of superlinear, we need to compute this limit. We need to compute this limit. Now, I assume xn, this sequence, the convergence rate is quadratic. Okay. Number 3. Yeah. Let me give a name to this limit. Okay. Number 3. I assume number 3 is true. Then conclusion is quadratic convergence must be superlinear. How to prove? How to prove? According to the definition of superlinear, we need to compute this limit. Now, compute this limit. Let me rewrite the function. Xn minus xn square times xn minus x star. Because xn, the convergence is quadratic, so this ratio approaches some positive number c. Xn minus x, this approaches 0 because equation number 1. I assume xn converges to x star. So therefore, this limit is c times 0 is 0. Therefore, conclusion convergence must be a linear, a superlinear. Must be a super linear convergence. Yeah, this is quadratic convergence. In general, let me extend quadratic convergence. Number 4, if I compare the current distance with previous distance, the power is alpha. Okay. Now net n approaches infinity. If the ratio approach some number c, where c greater than 0, any positive number, okay. Then in this case, we say that okay, the rate of convergence of the limit in equation 1. The limit in equation 1 is this limit. The rate of convergence is order alpha. So quadratic convergence is order 2 convergence. This is topic 1. Some terminologies that describe how fast a sequence converge to some number. Now, second topic. Let me see what is the second topic. Compare two sequences. In topic 1, we only focus on a single sequence. Now, compare two sequences. Topic 2. Compare two sequences. Okay. Suppose we are given two sequences. Let xn be the first sequence. Yn second sequence. Okay, now definitions. Number 1, if you can find some number c, some constant c, of course, greater than 0. If there is a constant c greater than 0, such that compare xn and yn. Okay, now let me take a ratio. Absolute value of xn over yn less than or equal to c. For we don't require this inequality holds for all n. We only require for all n large enough. When n is small, this inequality may be not true, but from some n. And after the n, this inequality should be true. Okay, then in this case, then we write a notation. Xn is bit O Yn. Yeah. So what this notation means? This notation means we have two sequences, Xn and Yn. When n large enough, this inequality is true for some constant c. This is the meaning of BO notation. Actually, we often use this notation, BO notation. Definition number 2, a little o notation. If now I also compare Xn, Yn. Take a ratio. Okay, when n approaches infinity, this ratio approaches 0. Then this case, we write Xn is little o of Yn. If Xn converges to 0, Yn converges 0, then little o means Xn converges to 0 faster than Yn. How about BO? BO says that Xn and Yn, suppose these two sequences converge to 0. Then BO notation says that Xn converges to 0 not slower than Yn converges to 0. This is what BO means. But anyway, definition is here. We often, when we do homeworks, we need to refer to the definitions. Let me show you examples about BO and little o. Example 1. Under topic 2. Okay, A. Consider these two sequences, n plus 1 over n squared and 1 over n is two sequences. Now let me make a ratio over 1 over n. Then let me make a ratio. Then after some basic algebra, then we see that this is a 1 plus 1 over n, then less than 2. This inequality true for any n, actually. Not just n large enough, for any n. This is true. So therefore, we have, by the BO notation, if we can find some constant c so that this is true for n large enough, then we have BO. The constant c now is 2. So therefore, we can write that n plus 1 n squared is BO and 1 over n. 1 over n converges to 0. N plus 1 over n squared also converges 0. BO means n plus 1 over n squared converges to 0 not slower than 1 over n converges to 0. A, now B. B. Consider these two sequences and lateral log of n and 1 over n. Okay, now let me compare these two sequences. Compare the general term 1 over 1 lateral of n over 1 over n. Then cancel n. It is 1 over n. Now take limit. Take limit. Then this is 0. So we have a little o rotation holes. Little o, yeah. Little o means xn over yn. When n approaches infinity, the limit is 0. Then we have little o. Then we have 1 over n natural log of n is little o, 1 over n. Yeah, this sequence fast converges to 0 faster than 1 over n converges to 0 compared to sequences. Example A, B, C. Say C. 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 Consider 1 over En is sequence and 1 over n squared is sequence. Both these two sequences converge to 0. Which one is faster? Okay, now let me compare the general term 1 over n over 1 over n squared. Then this is n squared En. Let me compute the limit because I have seen the limit is 0. How to find this limit? How to find this limit? L'Hopital's rule. L'Hopital's rule. Take derivative with respect to n. Then we get that the limit is 0. So therefore, 1 over En is sequence, converges to 0 faster than 1 over n squared. So we have 1 over En is little o, 1 over n squared. Okay. This is about, it turns out that there are one more example. Yeah, this example is about Taylor's series. Example 2. Example 2. By Taylor's theorem. By Taylor's theorem, En, this function, I can expand it into a polynomial about 0. About 0. Expand this about 0. This is 1 over 1 x1 1 over 2 x squared and so on. 1 over n xn, then plus error term. Okay, where the error is n plus 1 over n. E sine, what sine? I don't know. I only know sine is a point between 0 and x times xn plus 1. Okay. Okay, now first case, I set x to 0.5. Then consider these two sequences. Okay, the first one is a E.5 minus. Let me move the polynomial to the left-hand side. How about let me use a sigma notation, k from 0 to n, 1 over k, then x is 0.5 to k. Yeah, this is a sequence. The term, each number depends on n. And I compare this sequence with 1 over n plus 1. Factorial this sequence. Okay. Now let me compare. Compare the general term E.5 minus sigma k from 0 to n, k factorial 0.5 k. Then over 1 over n plus 1 factorial. Yeah, absolute value. Okay. Then the numerator by Taylor's series, the top is En 0.5 absolute value. Yeah, absolute value. But 1 over n plus 1 factorial is a positive number, so it doesn't matter absolute value or not. Okay. Now plug in here. Then we get 1 over n E sine 0.5 n plus 1, then over 1 over n plus 1 factorial. Now cancel n plus 1 factorial, absolute value. But both are positive numbers, so it doesn't matter. So cancel. Then we get E sine 0.5 n plus 1. So this is a less than E sine, right? 0.5 to n plus 1 less than 1. Sine is a number between 0 and 0.5. So this number must be less than E, must be less than E. So therefore, we have this sequence is a bit O of this sequence because we find constant E, so that this inequality is true. So by definition, right? By definition, let me use a different color. Yeah, this sequence is bit O of this sequence. So that means that the left sequence converges to 0 at least as faster as this sequence converges to 0, BO. So to study mathematics, definitions are most important. Always refer to definitions. And this is all for today's class.